As an overview, this is what I'm going to cover in this talk. So the basics of what is HTTPS. Everybody might recognize HTTPS from the browser and have a good sense of what it is, but I'll go over the basics again and go into a little bit more detail about what protocol versions there are, what Cipher Suites there are, and the whole point of this talk is how to configure NGINX to set your site up or service up with HTTPS. Beyond that, there's the question of using HTTPS as a proxy. So if your NGINX is in front of another application, how do you set NGINX up to act as an HTTPS client? And from there, I'll go into some ways that you can check your configuration to see that it is the most secure and the most up-to-date, as well as some bonus topics that help you get the A+ that you need in security. So, as you might guess, HTTPS is HTTP plus S, and S stands for security. And in the case of the web, this is two protocols called SSL or TLS. They're kind of used interchangeably. I'll go into that a little bit later. But it's a security layer that sits on top of your communication. If you think in the OSI so the OSI stratum, it sits below layer 7 in something called layer 6, the presentation layer. And what it provides to you is, between a client and a server, is confidentiality of data. So everything that's sent from the client to the server and back is fully encrypted so that the only two people that know how to read it are the client and the server. It also provides a form of authentication where the client can know that the server is exactly who it says it is. And these are all intertwined in the concept of the handshake. And this is your SSL TLS handshake. It's a little complicated. There's a lot of moving parts, but essentially, if you look, take a step back, it's an extra 1 or 2 round trips between the client and the server that send cryptographic information. In this case, you have several options right here. There's server randoms, there's client randoms. This is all kind of deep stuff you don't really need to know. All you need to know is that the server itself sends a public key, and the client and server establish a shared secret that they can use to encrypt the communication. So all the communication between the visitor and the server is encrypted with a symmetric key, meaning both parties have the same key, and it's also there's an integrity key. So in this case, an HMAC. But I'll skip over this diagram for now and go to the more salient question of why set up HTTPS. Well, the main reason is user privacy. And in the case of service-to-service communication, it's privacy of information. How much do you trust the networks that you're using to transit this information? Do you trust these networks to be to not inject things into your traffic, to be able to read what gets transmitted over? Also recently, if you're using this for a public website, it provides an SEO advantage. So Google will more highly rank sites that support HTTPS than those that do not. And another thing you can do for HTTPS, and this is one of the main use cases for NGINX, is to put it in front of services that don't necessarily support HTTPS natively or don't support the most modern, up-to-date version of SSL and TLS. So what you get with NGINX is the best state-of-the-art implementations of all the crypto algorithms that you don't really need to think about. And in general, it's good practice. So if someone's going to a site, they like to see that little happy lock icon. And in this case, this is nginx.com, which has HTTPS enabled, as well as HSTs, a feature I'll talk about later, which means that you can't really go to the regular HTTP version of the site anymore. The browser knows to always go to the HTTPS. Another thing you see here is there's a nice NGINX Inc. with the US there. That just shows that this is a extended validation cert. Essentially, the certificate that says NGINX is who it says it is. They paid a little bit extra for that and did some vetting. But it's not all roses. There are some downsides. Specifically, there is a little bit of operational complexity. You have to manage certificates, and you have to make sure that these continue to be up to date, and you need to have administrators who are trusted to hold on to the private key material. When you connect to a site over HTTPS, the first time it can be a little bit slower. If you're not necessarily physically close, then on top of the TCP handshake, there's the SSL handshake, which I mentioned, which adds at least 2 round trips. So there is a slight hurt to latency there, but this can be mitigated by several more advanced features of SSL, such as Speedy, which I won't go into. But in the end, HTTPS can be as fast as HTTP, but sometimes it isn't. There's also the cost on your servers to actually do the crypto. This was brought up as kind of an excuse or a reason to not do HTTPS a long time, but it's less and less applicable as the latest generation of Intel servers can do the type of crypto you need for HTTPS very, very, very quickly with almost no cost. So actually encrypting data in transit is basically free in modern hardware. So if you want to set up HTTPS for your service or your website, you need to make a couple choices and obtain a couple things. So the first is which protocols you want to support. The second is which ciphers you want to support, and I'll go into what that means. And also a certificate and a corresponding private key that is, and this is an important part, trusted by a third-party certificate authority that your clients trust. So I'll go into that in a little bit later, but first, let's talk about protocol versions. So a bit of history. HTTPS is HTTP plus the S, and the S has been changing. It's something that's evolved over time. Originally, SSL v1 was a protocol invented at Netscape, and there's a famous anecdote where Mark Andreessen was presenting it at MIT, and someone in the audience broke it with a pencil description of how you break the cryptographic algorithm. So that one didn't last very long, and eventually they released SSL2 in 1995, and this was essentially the start of the encrypted web. This is what enabled e-commerce and people to be able to submit passwords and credit cards online and be at least reasonably comfortable with doing so. SSL3 followed very soon, and this was a complete rewrite by Paul Coker and others. And this was a pretty solid protocol. In fact, the IETF took SSL3 and kind of mulled it over and worked it into what was not a Netscape-specific algorithm, but something for the wider audience called TLS, Transport Layer Security. Oh yeah, and SSL stands for Secure Socket Layer. And that's kind of the concept that people had at the time, but Transport Layer Security is what they call it now. It's a little bit confusing. TLS 1.0 is essentially exactly the same as SSL v3. It's just one or two little tweaks that the IEF took to standardize it. And if you actually deeply look into the protocol itself, the version number in TLS 1.0 is actually SSL 3.1. So you can kind of think of this as a continuum. But eventually IETF came up with new versions, 1.1, which was just a few minor tweaks, and then 1.2, which introduced some new cryptographic topics. But looking at this, you think, okay, well, some clients support these, some clients support more modern ones depending on where they come out. You can kind of compare with the years. But in terms of a security sense, most of these have been broken in a significant way or another. So SSL v2 is really not recommended. It was broken a long time ago. It's not cryptographically safe. SSL v3, people had been using it all the way up until just over a year ago, just under a year ago actually, when a cryptographic attack that was essentially 10 years old got rediscovered and was found to break all of SSL v3. TLS 1.0 and 1.1 are generally safe, and the latest one, 1.2, is the only one that doesn't have any known attacks against it. TLS has kind of a modeled history and not really the best security record, but it's the best that we have when it comes to interoperability with browsers and with services, and it's built into almost everything. So TLS 1.2 is the way to go. If you look on the web right now in terms of percentage of visitors, there's only certain versions that introduced 1.2, and these are actually pretty recent versions. And it works out to about 75% of traffic. So if you're going to set up your server and you choose to go 1.2 only, you're really eliminating a lot of your audience. So it's not necessarily the best move unless you are super security conscious and okay with letting wide swaths of people who aren't using, say, Internet Explorer 11 or later to use it. On the plus side, or not on the plus side, but on the other side of the coin, certain operating systems, platforms are starting to prefer TLS 1.2. So iOS 9 just came out with something called App Transport Security, and in it, it requires the server to support TLS 1.2. So the industry is moving forward towards this standard. In any case, TLS 1.0, that's the last one that's really secure. Basically works with everything except for Windows XP SP2. And there's not much you can say about this. It's end of life, but it's still used in different parts of the world. You might want to consider using SSL 3 if you really, really need to reach this audience, or corporate environments that have this very old version of Windows, and there's a missing S in this slide. So there's a site called SSL Labs. I'll kind of go more in detail into that can rate your site. And if you're configuring SSL, if you choose SSL TLS 1.2 only, you get an A. If you have only TLS, you get an A. If you go back to supporting SSL 3, it's risky, so you get a C. So this is what you have to consider when choosing your protocols. Now let's go into Cipher Suites. Now, what is this? What is a Cipher Suite? Well, there's various cryptographic algorithms that SSL, TLS, HTTPS uses to establish connections, and it's really an alphabet soup. You can see there's all these different acronyms. What do they mean? I can break it down. Essentially, the first one is the key exchange. There's an algorithm that the two parties use to exchange keys. In this case, it's based on the Diffie-Hellman algorithm. The second term here is what type of key is in your certificate. So every certificate has a public key of a certain type. In this case, it's RSA. The third piece is your transport cipher. So what is the encryption algorithm used to encrypt all the data? There's a lot of different pieces that go into this, but AES GCM, as I mentioned, this is the most secure cipher, and this is actually something that Intel processors do at almost zero cost. So this is a pretty cheap and solid cipher to use. And the last one is integrity. So as I mentioned, messages have a hash that goes along with them to make sure they haven't been tampered. But if it's encrypted and with integrity, you can go from there. Now, not all browsers and servers have the same list of ciphers they support, and this is called protocol flexibility. And essentially what you want to do as a server, what a server does is the client says, hey, this is all I support. Server says, okay, of those, I know about 5 of them. I'll pick my favorite. And so, for example, if the client says, these are the ones I support in this order, the server only supports 2, and then it'll just pick its favorite. This is really not a really big matter of debate, but there's a lot of options that you have out there. CloudFlare uses this Cipher Suite list, and you can find it on github.com/cloudflare/SSL config, and we have it in an NGINX configuration format. And these are the ones we recommend. These are the ones that all sites that are on Cloudflare end up using. So there's a cool new cipher called Cha-Cha-20. That's not supported in mainline NGINX yet, but we're pushing to do it. Everything else here you can use. Mozilla also has their own recommendations on this, and you can go to their site, which is the server-side TLS site, and they will generate an SSL configuration for you for NGINX, or for whatever web browser or whatever web server you might be using. So that's the Cipher Suites. So we have a protocol set, Cipher Suites set, now certificates. This is the most important part of HTTPS. This is what identifies you as a site to your customer. And what's in a certificate? Well, there's your name, who you are, what domain names your site is valid for, when the certificate is valid for itself, the public key for which the customer can use to validate anything that you sign with it, and then there is a digital signature, kind of a stamp from a public certificate authority that is someone who says, yes, this is a real certificate, this is the person actually owns this DNS name, and it's valid from these points. So what makes a certificate trusted? Well, this is a breakdown of all the certificates on the internet right now, who most of them are signed by. So there's some common names in here. Symantec has bought several of these certificate authorities, including GeoTrust, VeriSign, and others. GoDaddy has one, Komodo, GlobalSign, DigiCert. These are all kind of big companies that are trusted, and most importantly, their certificates are trusted by browsers. So if Symantec says this certificate is good, via the process of someone buying a certificate from them, then browsers will present the green lock and say, yes, okay, I believe you. This is really who you say you are. And how you get a certificate is, well, you have to create a private key or a pair of keys, and then send off your public key to the certificate authority to rubber stamp and turn into a certificate. Now, this usually costs a bit of money. There are free ways to do it, but essentially, the private key you have to keep private, and the only person or the only entity that should have a hold of this is your administrator, and your web server itself will need this. There are several ways to create these key pairs. We built a tool at CloudFlare called SSL, which is a way to generate these keys and what's called a CSR, which is a certificate signing request. And this is essentially the way that you package your public key to the certificate authority to create a cert from. And yeah, there's OpenSSL, CFSSL, several ways to do this. And if you want a free one, the current most well-known site is StartSSL.com. So they will give a free site for your certificate, valid for a year. The UI is a little bit less than nice. So good luck trying to get through this. There's other talks later today about the future of certificate authorities, and it's looking that getting a certificate will be something that is less and less costly as time goes forward. There are proposals for free certificate authorities. So right now, you can pay for a nice experience with Komodo or DigiCert or GlobalSign or whoever, or you can go the free route and go to StartSSL. Now, certificates don't get signed directly by the certificate authority. There's this kind of chain of trust that gets built up. So if you have a certificate, it's usually signed by an intermediate certificate authority, and that intermediate certificate authority is signed by the real certificate authority. So in this case, you can kind of think of it as, this says CloudFlare, but imagine this is a certificate authority, is you get a certificate and you have this whole chain of certificates that you present. And not all browsers necessarily know what the next one in the chain is, and browsers are really only bundled with the top, the real offline root certificates. So when you get a certificate, you also need to have the whole chain of trust along with it. There's a tool we built called CFSSL Bundle that allows you to create this if your CA doesn't give it to you. Typically, your CA will give you this chain. So now on the good part, now that all the kind of theory is aside, how do you take these options and configure NGINX? Well, there are some basic primitives here that you can use, and they are SSL Certificate, SSL Certificate Key, SSL Protocols, and Ciphers. They correspond to exactly what we were talking about. Before you start, NGINX, the way it does TLS is with OpenSSL, which is a tool I'm sure a library actually that you've heard about in the news. It was famous for Heartbleed and several other vulnerabilities that came out. It really is the most widely used crypto library built in, and this is what NGINX uses for crypto, for better or for worse. So one thing to do on your server is to check which version of OpenSSL you're using, and you probably want to not use one that's, say, 0.98 and something in the 101p or 102 range is where you want to be, because they've fixed a lot of bugs over the years, and the most recent versions are, I would say, less full of bugs. Never know when the next OpenSSL bug drops, but at least right now it's pretty solid, the 101p. And it also has all the modern crypto. So when you set up your server section in NGINX, it's really this. SSL certificate is your chain of certificates. This is your certificate plus all of the chain of trust all the way up to the root. And then you also provide your private key. And these are paths. And there are some extra options you can add having to do with session resumption. And as I mentioned before, when you first establish a TLS connection, there is an extra 2 round trips because you have to do an entire handshake and exchange certificates and all these sort of things. If you've previously connected with a client and they've cached the key that is used for the session transport, you can just resume that session. And this is a feature called session resumption. And if you look right here, it really, you just need a timeout to say how long you want to keep sessions for on your side, and then how big of a cache for these sessions you can have. In this case, the default is 50 megs. That should last you for a long time. And a shared cache is preferred because then you can share them between all your NGINX workers. So that if one of your workers was the one that originally made the connection and a second connection gets made to a different NGINX worker, you can still resume the connection. And this really speeds things up. There's a nice talk tomorrow by one of my coworkers, Zilin, about session resumption and all the work that we've done to make session resumption safe. There's also another option called session tickets. This is less widely used. It's only used in Chrome and Firefox, but essentially does the same thing. There's instructions on how to do this. You have to generate a random 48-byte file, but I would recommend sticking just with session caching for now. As a pretty obvious next step is you have to list the protocols you want to support and the ciphers. So in this case, these are the ones that CloudFlare supported ciphers, CloudFlare recommended, and the TLS protocols starting with 1 all the way up to 2. I mentioned how you negotiate which cipher you choose. You can prefer the client's choice or the server's choice. It's always better to prefer the server's choice. So there's a directive here, SSL prefer server ciphers. Always turn this on. Now, if you have multiple sites and you have them using the same certificate, you can actually break up your HTTP definition to have your SSL certificates on the top level and then different servers on the bottom levels, and it'll work appropriately. So the one thing that you have to keep in mind here is if you have example.com and example.org, you have to have one certificate that contains both of those names. That's valid for both those names for this to work. And that's basically it. That's the basics of setting up NGINX for HTTPS. Now, the more advanced topics are how do you use NGINX as a proxy behind other HTTPS services? And what we'd like to call this is backend encryption. So your visitor comes to your NGINX server, and this is fully encrypted. What happens behind NGINX? Well, NGINX has to kind of act, in this case, as the browser to whatever your backend service is. Now, this can be configured in NGINX in a very similar way. There's similar directives to SSL protocols, SSL ciphers. In this case, it's just you put it under proxy. So proxy SSL protocols, proxy SSL ciphers. These are the ones that you're going to use as a client to NGINX to whatever. It could be another NGINX, it could be another service behind, but this is how you configure this to work. And I would recommend using the exact same set of ciphers and same set of protocols. The main difference here is that as a client, as I mentioned, the client authenticates the server. So in the case of a browser, you have a bundle of certificate authorities that you trust, and as NGINX, the client, you need to have this set of certificate authorities that you trust. And there are two different ways or two different philosophies that you can use to approach this. And one is to create your own internal certificate authority and manage it in-house. This is a little bit trickier, but it is cheaper and it's more easy to manage because you can issue a certificate for any one of your services, whatever they're named, and have them issued to a certificate authority that you own and have full control over. In that case, this proxy SSL trusted certificate would be set to your certificate authority. Alternatively, you can do the same technique that I described for NGINX, which is you can buy certs. Just buy a certificate for all of your services, and then if your NGINX needs to trust them, then it can trust the same set of certificate authorities that the browsers trust. And so for Ubuntu, there's a list on disk, and there's a place on disk that holds all these certificates for basically every platform. But if you are building a large set of services that are going to need to talk to each other, it is hard to get certificates issued for these domains. You have to prove ownership to the certificate authority to actually get the certificate. So if you can, I recommend the internal CA mechanism. The tough part about this is really how do you keep this certificate authority safe? How do you keep the private key of that certificate authority safe? And you can do it by having an offline computer and a special administrator to do that. But in either case, there are some challenges. Okay, so you have NGINX set up with HTTPS. How do you check that it's configured correctly? Well, one of the favorite tools for people checking websites is SSL Labs. Now, SSL Labs, this is a site run by Qualys, and you just type in your domain, and it will run a full suite of every type of browser, every type of SSL connection, and it'll tell you what you have set up correctly and what you have not. So in this case, we checked a site, I think it was, there's a site called badssl.com, which essentially enumerates all the different ways that you can mess up your HTTPS configuration. And you can scan each one of those with SSL Labs, and it'll tell you what's wrong with each one. So in this case, the grade was given C because it supports SSL 3, which I mentioned is a protocol that is broken. But you do need for backwards compatibility with Windows XP 2, but you don't really need that. There's also several other things that it mentions here that you can kind of fix up. But in the description of how I set up NGINX in my talk, you're basically going to get an A if you set it up that way. And that means the certificate, protocol support, key exchange, cipher strength, these are all kind of top-notch. We also built, so if this works great for public websites. If you have services that are behind a firewall or behind an NGINX, we built this tool called SSL Scam, which will, you can use it inside your internal infrastructure. It's open source. You can build it. It's on GitHub. And it will do essentially the same thing that SSL Labs does, but inside your infrastructure. And it'll tell you what's right, what's wrong with your configuration. So this is how you get an A, but what about an A+? Turns out that SSL Labs does give an A+ every once in a while, and that's when you have a feature called HSTs, which is Hypertext Strict Transport Security. Essentially, what this is an HTTP header you can add on your requests that tells the browser to always reach this site over HTTPS. Even if they originally reached it over HTTP, whenever you go to HTTP, always redirect to HTTPS. Don't ever read the HTTP site. And this is something that you can use, but it's actually a little bit dangerous because if your SSL configuration breaks, then, or say a certificate expires, then there's no way for visitors to go to your plain HTTP version of the site. There's also some more advanced things that you can do here, and that's adding your site to a preload list. So both Chrome and Firefox, you can check the header to see if something should be always HTTPS, but they also have a list baked into the browser. So if you sign up for this, then you can say Chrome will never ever access my site over HTTP. And this will give you the nice A+ on if everything else is correct on SSL Labs. If you have HSTs set correctly with include subdomains, which means it applies to all subdomains, and it has at least a 6-month expiration period, which this is what makes it very risky, because if you change your configuration, browsers are going to remember this for 6 months. So you really have to keep your HTTPS configuration working. But the reason that this is a good thing is that every once in a while, HTTP, as I mentioned, is less secure. So someone in the middle can, say, modify, whether it's your ISP or anybody, if you're in a coffee shop, can kind of modify things and inject cookies or do anything to your site. And with HSTS, the browser will never have a chance to even go to your HTTP site. So people can't mess with your site from that regard. So HSTS is a pretty solid thing to do. As I mentioned, there are several risks. But to set it up, this is just an example, but in your server config in NGINX, just add a header that says strict transport security and give it a max age. And in this case, this is in seconds, so this is 6 months in seconds. That's the minimum you need for the preload list. And you can add other directives here, such as include subdomains and preload, which means that it's acceptable to take this and add it to a preload list. So that's how you get the A+. Here's just another bonus feature that some people like to use, and it can help actually speed up the connection. As I mentioned before, there's quite a few back and forths that you need to set up a TLS connection. What I didn't mention was that these certificates, not only can they expire to go bad, they can be revoked. So if you lose track of your private key, or there's a breach, or someone has managed to own your private key, then you have to go to your certificate authority and revoke this key. Now, there are several mechanisms for telling a browser that a certificate is revoked. They're all a little sketchy, but the most popular one is OCSP, which is the Online Certificate Status Protocol. And what happens is when the browser receives a certificate, it also has to check to see if it's been revoked or not. So it contacts the certificate authority and says, hey, is this certificate still good? And they'll say yes or no. And this in itself is another set of connections. So you have to look up the DNS of the CA, you have to connect to the CA, and it's really kind of an additional slowdown for your site. So not only is it 3 round trips to do HTTPS, you have to get the OCSP. So what OCSP stapling is it allows the server to grab this proof that the certificate is not expired for you. And in the background, it'll fetch this OCSP response that says, yes, the certificate is good, and then put it inside the handshake. So then the client doesn't have to actually reach out to the CA and get it. And this makes connections around, if you do the math on this is obviously back of the envelope type of stuff, but it can save around 30% in terms of connecting to a site, 30% time. And this is pretty easy to set up with NGINX as well. There's a directive called OCSP stapling. Stapling verify means that you verify the certificate after you staple it. And as I mentioned before, with the proxy, you have to trust the CA. So you can just get a file from your CA to add into this trusted certificates section. So that brings us basically to the end of this session. This is how you configure NGINX and OCSP stapling, HSTS, and SSL proxying. So any questions? Yeah, so the question is, do I have a link to my slides? And I will add the slides online and provide a link. You can go to my Twitter handle here. I'll post it within a few days. I'll put these slides up. Yeah, I realize there's a bunch of directives on the slides that you probably want to copy down, that taking a photo is not the most accurate, most efficient way of doing so. Okay, any other questions? So the question is this how it's going to be, or is it going to be changing over time? Which is a really good question, because as I mentioned, TLS 1.2 is the latest and greatest. This was 2008. They're coming out with a new version, TLS 1.3, so this is probably going to be coming out within the next year. So this applies to right now, and HTTPS is a changing landscape. So threats that we didn't know about 2 years ago have completely changed the way that you would configure something now than you would have 2 years ago. So I would expect this to change going forward, and for people setting up HTTPS to be aware of the changes in the industry. If there are big attacks, then learn what the new best practices are. So it's constantly changing. But for now, this is the way to go. Anybody else? Okay, well, thank you very much.